Welcome to Lab Life with the Air Force Research Laboratory.
Hi, I'm Michelle.
And I'm Kenneth. Hello, folks. Today we are joined by Dr. Benji Maruyama from the Air Force Research Laboratory, Dr. Eric Stach from the University of Pennsylvania, and Dr. Alexis Lewis from the National Science Foundation to discuss autonomous research systems, the National Science Foundation, and how a workshop in West Philadelphia brought all of them together.
In 3, 2, 1.
Doctors, welcome to the podcast. Thanks for joining us today.
Great to be here.
Thank you.
I'm going to be direct with our listeners right now. I normally write my own jokes, but today, Kenneth, my co-host, wrote this joke for me where I'm supposed to kick off the podcast making an iRobot reference. It's been a while. It's a Will Smith movie, and I think he saves the world from robots. But, to transition and kick off to the meat of our podcast, Alexis, Benji, Eric, you're smart people working on autonomous research. So we're talking robots, robots that might do cool things like teach themselves to grow carbon nanotubes at controlled rates. That said, what you're working on, does it have the potential to become an iRobot situation?
I totally misread that as iRobot, the company that makes Roomba. So that's a completely different context where thinking about an automated task for sure has some link, some relevance there.
Yeah, I think there is a good link in that we're thinking about, when we hear autonomous robots, we think about robots going off on their own. And what we're talking about is really robots, research robots working with human researchers to do things faster and better.
A slightly related question. We know some of you have Philadelphia roots, and we just mentioned Will Smith. So can any of you rap the Fresh Prince of Bel-Air song?
I know the lyrics, but I will not subject anyone to my singing.
No, I'm a strict Public Enemy connoisseur. That's about as far as I go.
Honestly, then we could have after the podcast is done, maybe for our listeners, if they really ask, maybe we'll have a separate section for the podcast, one that maybe people can hear later on when we all sing along. We'll put that in the wings for now. We'll see what attention we get. But that's honestly awesome to hear that you guys not only have a connection from Philadelphia, obviously with things in terms of robotics, autonomous work, AI research, and we have a lot of topics we're covering now, but let's kind of take a step back and get an idea of who all of our speakers are today. So starting with you, Alexis, can you kind of give us an idea of who you are and your area of expertise?
Absolutely. Thanks, Ken. So I'm Alexis Lewis, West Philadelphia, born and raised. But right now I'm the Deputy Division Director in the Division of Civil Mechanical and Manufacturing Innovation and the Engineering Directorate at the National Science Foundation. So I've been with NSF about 7 years, and I've worn many hats, including working as a program director in the Materials Processing Program, Advanced Manufacturing, and a stint in the Office of Advanced Cyber Infrastructure. One of the many hats I've worn fell under one of the major thrusts at NSF, which we've been calling the big ideas for future innovation, one called Harnessing the Data Revolution. And that's where I started thinking about things like how data science, artificial intelligence, and machine learning can enable new discovery in engineering.
That's cool. What a great name too, Harnessing the Data Revolution. Like that really does evoke a very powerful image.
Yeah.
Awesome. So we'll go down then. So Benji, would you be able to tell us who you are and your area of expertise?
Yeah, thanks, Ken. So Benji Maruyama. I also grew up in West Philly and transplanted to Ohio a long time ago, and have been working at the Air Force Research Lab for several decades. So I'm a materials researcher, and along the way got into trying to figure out how to do research faster, and teamed up with some people who really understood robotics. And so one of my titles is Autonomous Materials Research Lead.
Fantastic. And we'll end here then with Eric. Who are you and what is your area of expertise?
Sure. Hi, my name is Eric Stach. I'm a professor at the University of Pennsylvania in West Philadelphia, and I have an expertise in materials characterization. I've worked with Benji for 16, 17 years now. And I also lead the Laboratory for Research on the Structure of Matter, which is an NSF-funded materials research, science, and engineering center. One of the kind of activities that we do within the MRSEX is we bring people together to think about ways that we can impact the broader community. And that's in some ways how we got involved with this workshop and paper.
So I'm glad you mentioned the workshop. So that was the next connecting point we had to bring all of you together outside of West Philadelphia. Was the idea that there was this workshop that you were all able to kind of collaborate on and got closer for the project we're talking about today, or the paper. So starting with you, Benji, can you kind of talk about this workshop and how it connected all of you?
So our co-organizers with Eric were folks from NIST. So that's Jason Hattrick-Simpers, Gilad Kuzni, and Brian DeCoste. And so we were very happy to have NIST partnership to put on this workshop. And we got together and really thought about what do we need to do to essentially set out a vision for the community, figure out what kinds of things need to be done to move us forward, what kinds of investments need to be made, and how to start going about executing that. And so Eric was gracious enough to host us and help get us going at the Singh Center for Nanotechnology at the University of Pennsylvania. And so we had a great 2.5-day workshop with really the leaders and the thought leaders in this nascent field.
We were also very fortunate to be able to bring, I think, a pretty diverse group of people together to contribute to this. And that included folks that were actively in the field of doing materials research in this mode, but also a number of experts who come from the broader artificial intelligence community, from industry, practitioners in industry, as well as the national laboratories and academia. And I think that one of the results of this was that we were able to kind of pull together a summary that we wrote up in this paper. That's kind of what this is something really pointing towards, where we were able to define, I think, fairly well how the different parts of the community need to work together to advance the overall goals.
Yeah, one thing that was of particular interest to us at NSF is that collaboration, how folks work together, and thinking about that in terms of both the research and of the workforce, the students and the training, but also today's workers and how they will interact with automation. So that's something that NSF has a strong interest in and a number of programs focused around. And so that was part of what brought me to the table for the conversation.
So speaking of other connections then, with the National Science Foundation for you, Alexis, for people who may not be familiar, could you kind of talk about what their mission statement is and how really this connection with the research makes sense between us and the foundation?
Absolutely, yeah. So NSF, the National Science Foundation, has a mission to promote the progress of science. And really, this allows us and our researchers to think about how research will ultimately benefit the nation. So we think about that, again, in terms of research and in terms of education. And then, of course, how that benefits society. So I mentioned some of the big ideas for future investment. One of them was harnessing the data revolution. Another one is called the Future of Work at the Human Technology Frontier. And that is a program where different disciplines are being brought together to understand, among other things, how human workers will interact with things like autonomous systems. So we do have a number of programs that focus on that research on how to build the systems and how to understand the human behavior. From my perspective, again, the interest in the education and the training and kind of what we need to be doing now, teaching students who are in the classroom now, all the way from K to 12 through college, university, and advanced degrees, but also how to prepare the folks who are currently in the workforce for what is going to surely be a changing environment, a changing work environment.
And I just want to shout out to the NSF that helped me understand that science was cool with all the funding that you did for probably the PBS programs that I watched as a kid, because, that's probably why we have a lot of the researchers and scientists that we have on our teams today is because of outreach like that.
I hope so. I hope that the communication tools that are broadly spread around, including some of those great outreach tools, are still reaching kids today.
And that's a really cool element as well, that talking about these workshops, talking about how we connect with the future generation, it shows just how important the NSF is. And I was going to clarify that too for some of our listeners. So is the way you're actually making a lot of these connections you mentioned is through what courses or at least information you can send to these students? Then you said workshops for people in industry, like that's how you kind of bring these heads together?
There are a lot of different ways, actually. There is the investment in education explicitly and sort of understanding curricula and how we teach students, again, all the way from kindergarten through advanced degrees. And there's also the educational components that are linked to research projects. So for example, when graduate students work in research labs, there's a strong educational and training component there. And then there's thinking about the training in the current workforce. So maybe you're not necessarily a student in school, but we're all lifelong learners, and thinking about the kinds of things to really advance the economy and to help keep US workers sort of at the forefront. And what kinds of innovations do we need from a scientific and an engineering standpoint to help create that balance?
And now that we're kind of, caught up with some of your guys' day jobs and your roles, I'd like to jump in to the talking a little bit more about your collaborative paper. So it was published in the journal Matter. It's called Autonomous Experimentation Systems for Materials Development, a Community Perspective. We'll link to it in our show notes for our listeners so they can take a look at that. We also have some local press releases that condense some of your main talking points. Dr. Stach, could you, kick us off and talk about the paper?
Certainly. So the goal of this was to try to bring everyone together to put forward a vision for where the community exists at present in terms of capabilities, but more importantly, not so much as a review, but rather a forward-looking document, and to try to define where a variety of specific advances are needed, both in terms of the AI side of things, the algorithmic side of things, to understand how to better analyze data, make decisions, but also in terms of infrastructure investments that may be needed to improve our ability to conduct these sorts of experiments. And then we also spent a bit of the paper also thinking about the educational components that Alexis was just discussing. What is needed in terms of workforce development, and also as these tools come into being, how do they enable a broader participation of people in society into the process of doing research. If you have autonomous research and it goes the way we envision, we'll be able to explore ideas very quickly, increase the speed of research, but also perhaps even make it more available to people, where people could come in with an idea and access one of these tools and then pose questions and have them assist in the discovery process. So these were among the key points, I think, in the paper, mostly trying again to define where investments were needed and where we think opportunities are for both research and education.
We want to make sure that, with this, it's a great way to actually launch into the paper and get an understanding of your piece of it, Eric. So I want to go over to Benji then. Do you have any other comments on the paper itself and kind of the contributions we have, especially from the lab?
One thing that we did to start off is to describe what an autonomous experimentation system actually is. And so just to go over that kind of briefly, and really to set the scene even before that, if you were to follow a scientist around a lab today, you'd see them doing things like pipetting samples and grabbing samples and polishing them and putting them in microscopes. And it's very human-oriented, manual kinds of work. Despite the fact that we have now fabulous tools, we have microscopes. Eric's lab has microscopes that can see individual atoms. And so those advancements have been tremendous. But if you look at the process of how people actually do research, it hasn't changed for a really long time. And so the analogy I like to give is that if we were like farmers, we would be like farmers in the pre-industrial revolution era. So we would be walking around with hand tools and oxen if we were lucky. And today's farmers, as we know, have tractors to do that manual labor, but they also use GPS guidance to make sure that they're going along the perfect direction. And they are increasingly using artificial intelligence to guide timing and all of those kinds of decisions that they make to improve essentially their cognitive ability. So it's augmenting their experience and their expertise with artificial intelligence. So we want to do that for science. And so the idea here is that we build robots that can do those things in automated fashion. So turning knobs, changing temperature, taking images. And that's sort of the manual part of things, but the cognitive part of things, the brain work, is really thinking about, okay, I just did these experiments, now I know something more, what should I do next? And so that's where the autonomy and artificial intelligence comes in, is that those algorithms can then help reason and figuring out new things to do to make that experiment the best next experiment that you can do. And if we do that over and over again in hundreds or thousands of iterations, we end up being able to do science much faster than we're currently able to do. And much faster is, we're still working that out, but we're already at a factor of 10 or 100 times faster. We might get even orders of magnitude beyond that. So that's kind of the value proposition, is that we can use these research robots to essentially multiply our human scientist effort, both in the manual side and in the cognitive side. And so now within the community, and as described in the paper, there are a number of groups who have demonstrated that. So we were the first ones at Air Force Research Lab to do that in the area of materials, but now others have done that in other areas as well. And so it's really starting to blossom. It's a very exciting time in autonomous experimentation, because people are really realizing the value and jumping in and doing more and many exciting things to get things going.
I mean, you're hitting a really cool topic there that I think is fascinating. This idea that you mentioned, especially with the way we conduct things in labs, that we aren't as autonomous as other areas, like farming, for instance. So it is amazing to think that once this scales up, like you mentioned, this really will change not only the materials world, but a lot of the testing world. And having that partner, like having that actual autonomous partner who you can say, like, hey, here's like a batch test I want to give you, or a certain experiment that you can take care of while I work on something else over here. And I mean, you're right. The work you can do is, I mean, you gave us a good idea of how many folds, or how much more efficient it's going to be. But until we really see it in action, I mean, I feel that's going to adapt even more in the future. So you're right. We're at the precipice of something incredible.
Yeah. And I would say, maybe just to add, there's a challenge out there. It's the Nobel Turing Challenge that was issued by Professor Kitano in Japan. And that challenge is, can a autonomous scientist win a Nobel Prize by the year 2050? And by the way, pass the Turing test. But I think that's a great way to crystallize where we want to go. And that is, can we use this autonomous experimentation approach as a way to do something that really is so important, so valuable, that it's worthy of a Nobel Prize?
Absolutely. And thinking about that too, even passing the Turing test and all these other stepping stones, that could be very interesting. I mean, do you feel we're actually on the right track then? Like by that period, do you think that's going to be a plausible outcome?
I do, absolutely. And in a sense, we really are at the early stages. But if we think of, I draw an analogy to Moore's Law. So Moore's Law was the increase in the speed of computer processing, or the number of transistors. And that went up exponentially. So every couple of years, right, the processing speed doubled for many years. What if we could do that for the speed of research? What if the speed of research increased by twofold or fivefold every couple of years? Imagine what you could do. It would be incredibly impactful. And that's the thing, is right now we think of technology as advancing really quickly, but scientific research is still painfully slow. And so what if, instead of spending your time washing test tubes and polishing samples, you were really thinking about the big brain work of what hypotheses do we want to test? What problems do we want to attack? And so I think that's really the far-term vision for this area.
Absolutely, yeah. The image always comes to mind with me, obviously not completely connected, but is the idea, like as a big Star Wars fan here, thinking about having my astromech as my co-pilot. If they're able to help fly my craft, I can go take care of other things in the back and make sure I can do more thoughtful creation or whatever I'm doing in my vessel. So again, not completely, the analogy kind of works, but either way, having an assistant. But before we go ahead, I want to make sure I go back to you, Alexis. With a collaborative paper, is there anything from the National Science Foundation side that you want to kind of add in for the story?
I think that, again, the education and training side of things is something that's really of interest to us, and the broader impacts. And, you mentioned having that assistant, right? This is something that we think about from a number of different perspectives. How can we enable new discovery, but also how can we broaden the participation in science and engineering? So Benji mentioned the tools that Eric has in his lab that can resolve atom level structure. And sometimes those samples that you look at require a lot of work, a lot of precision, maybe somebody doesn't drink a lot of coffee because you need a very steady hand, right?
In fact, it's best if you have one cup of coffee so that your hand becomes steady if you're a coffee addict, and then you do the work. I know that from strong experience.
Exactly. There are a number of aspects of this really high level scientific research that right now require certain physical attributes to be in the lab and to be able to handle specimens or to be able to maybe lift things. And to be able to automate that really can broaden the scope of people who can participate in this kind of work. And it might also lead to, more consistency from one sample to another. If instead of having that human factor, we've got a robot who repeats the task and does everything the same way, that helps us a little bit in understanding and removing some variables.
Yeah, just to build on Alexis's really important comment about access. So one of the interesting corollaries to Moore's law about the speed of research increasing is that the cost, for example, of transistors also went down exponentially, so that the computer that cost $2,000 cost $1,000, or you got twice the power for the same amount of money. So if we think about that for research, as it becomes for the same price of doing one experiment, you could do 10 or 100 experiments. All of a sudden, research effectively becomes cheaper. And so that makes it more accessible. It means that more people can participate in doing scientific research, which is also exciting, so that you can either get virtual access into a lab, or maybe like we're trying to do, we're building autonomous 3D printers that are low cost, that are a few $1,000s, maybe a few $100s, but that are fully autonomous and teach themselves how to print. So that really changes the game, because once things are cheaper, right? It used to be that computers were in mainframes and only a select few got them. And then they were laptops, but still they weren't affordable to all. If we can make research really inexpensive, then access really multiplies. And then we have more people doing scientific research. And that's very exciting, because we don't have all the best ideas. And so if we can have many more people bringing their ideas about what's important to do and how to do it, that really changes the game and is very exciting for me.
And this idea of accessibility and being able to kind of visualize the system is something that we're kind of trying to touch on for our listeners. So now that we have an idea of how the idea behind it and kind of the mission statement, if you will, what is the system going to look like? So let's say somebody actually is able to get these autonomous systems in their lab space. Is it variable depending on the mission? Is it easy, like you just got a box you can pop in there, plug in, and starts working? Like starting with you, Eric, can you kind of describe what this would look like?
Well, I think that's one of the challenges we were bringing forward within the paper, is that materials research has a variety of different topical areas. Not every single person's doing the same thing. And so there are common tools that we utilize. There's common analysis methods that are used in the field. And, we pointed to the need for increased open source and open access software, ability to share data. Again, these are key NSF themes as well, so that we have the ability to maybe plug and play a little bit. You design an experiment where you're taking a material and you're heating it under a flow of gas in order to achieve a different structure. And you need to know what the structure is, so you may have to find a way to analyze that using, say, X-rays. And so there's kind of some key pieces that need to link together and then be brought together as a system in order to do the analysis. And to some extent that requires the development and distribution of software for the analysis, for also the artificial intelligence piece, which takes the data and thinks its way through and says, based on the constraints that you've provided to me, here's the next most insightful thing to do. And I think all of these things are being developed by people within the community, many of whom were participants in the writing of this paper and in the workshop. And with time, you kind of hope that things become a bit more plug and play, as opposed to right now, where in the early stages of demonstration, people pick a topic, they build a system, and they demonstrate it in a single system. But we're hoping eventually there's networks of systems, and then eventually access to key tools, both nationally and internationally through the internet and the like, to do the work.
And I think an integral part of your paper also covers Aries Os. So how does this fit into the autonomous researching ecosystem?
Aries OS is essentially, we think of it as like an operating system, a framework, a software framework for people to build their own autonomous research robots. And what we realized as we were doing it is a couple of things. One is the software development, the investment in software development is significant. And so in order for each person to, each group to make their own research robot, if they have to start from scratch building their own software platform, that becomes expensive and it becomes a barrier. And so what we wanted to do is build a framework, which we're calling Aries OS, that is broadly applicable. So you start with an Aries OS and then you build the rest of your software for your particular research problem. And so I think of it as sort of like your phone OS, and my software engineers cringe when I say this, but basically if you have a phone which has an OS, you can write an app for that phone without having to get into the details of how the phone works and all of the communications and hardware, software, all that kind of stuff. You just think about the high level things that you want to worry about. And so we're hoping that with this Aries OS, which is now released as open source, and so you can, and we'll put a link for folks to access it, but you can access it and start to build your own research robot. Of course, people have to build the other modules for their particular problem, whether it's a hardware software plugin or a planner, so the artificial intelligence algorithm that makes the decisions for what to do next. So those kinds of things still need to be written. But the other part that we're hoping is, as a community effort, as more people write and hopefully contribute as open source their own modules, that people can use those, modify them, and contribute them back so that we end up with a community resource. And so everybody is helped and everybody is able to build their research robots faster and with a lower barrier to entry.
And that's really the why this went open source. That isn't just something that you kept to yourself, because it just multiplies the more people that have access to this, and you've decreased that barrier to entry.
Science is a group effort. And it's the problem is that it's so vast. There's so many problems that are worth working on that there are not enough of us to do it. And so I think the more people we can get involved, the younger that we can get people involved. So if we can get high school students involved in the research process, that helps everyone. And so I'm very excited to do this, and I'm hoping that a lot of people invest in. I would say there are other folks who have software as well. So there's software like ChemOS out of Toronto. There's KDL out of Glasgow. So there are other people who are developing software that's directed towards this kind of closed loop research. So I would say it's early days and it's very exciting.
You talk about like the students that are our future of science, and we really need to build that foundation. And I think everyone on this panel right now is investing in our future through youth. But when you talk about accessibility, so you were saying like these programs, this open source stuff, can even run on these relatively inexpensive, a 3D printer or something when we're talking about the materials world. And then you're training your 3D printer to print better. You gave this visual for me as like you're trying to print a straight line, and initially it's just a pile of spaghetti. But this is something this robot can help with?
Absolutely. Yeah, that's right. For folks who have gotten a 3D printer, a lot of people have the experience that they get the printer, they're super excited, they take it out of the box, they get it set up, and it doesn't work. And it turns out that there's a lot of tuning that has to happen for that printer. And that's for something that's already like, the printer, the filament that you're using. For us in the lab, we're developing new inks that nobody's ever used before. And so how do you figure out how to print with those? And that could take a couple of weeks. And so really what the idea behind AM Aries, Additive Manufacturing Aries, is again to reduce that barrier. So you get your new printer or a new ink, you set it up, you hit go, and Aries then iteratively prints something out, it takes a look at it, sees what happened, and says, oh, that didn't work, now let's try this. And does that, over, tens, hundreds of iterations of tries, and eventually it teaches itself, okay, these are the settings to use to print. And hopefully that means that now when you go to print that complex structure that might take hours to print, you're going to be successful. And so even outside of the materials development, we're hoping that this is helpful for other folks.
And that was something we wanted to kind of pull back on. We know you touched on it earlier, kind of talking about the system and now talking about Aries Os and how open source this is and connecting a lot of the community. A big aspect of the system is the idea of getting this kind of real-time diagnostics. So can you kind of touch on what that means exactly and why that's really going to change a lot for researchers?
So in many cases, in the course of doing materials research, you are asking questions regarding how you change your processing methodology, the application of heat, gases, liquid, corrosive, whatever, to alter the structure of the material, because the structure of the material is what determines the properties. This is kind of the core paradigm of material science. Processing leads to structure, leads to properties, leads to performance. And in the course of trying to get a material that performs better, you're being forced to go through a loop where you change processes in order to change structure and measure the properties. And the key points there are that you have to find ways of manipulating multiple competing processes to get the structure you want. And in many cases, by manipulating one parameter, you're also affecting others. And more importantly, there are many, many parameters often involved. So in conventional scientific research, we tend to move along one axis. We'll say, okay, let's change temperature. And then we'll go and measure things. And the point is that may also affect changes in the gas dynamics, other things. And so as a result, there's many complex and interrelated variables that are affecting the outcome. And the advantage to having a real-time diagnostic as well as a artificial intelligence approach is that it allows you to think through that multidimensional space in ways that is complex, if not impossible for a human to do. Matrix operations are things that computers do well. And so in some ways, what this enables for us is it enables us to be efficient at exploring those spaces, right? That's what leads to this increase in the speed of research and the outcomes of developments. But it also allows us, I think, and this is something that still we need to work through as a community, is how do you take advantage of the so-called black box of artificial intelligence that's taking and looking at these parameters and making decisions, and then using that to pull back into physics-based or chemistry-based, constraints on the system. And that's actually a really interesting area. It was, I think, one of the reasons we got a lot of attention at this workshop from some of the folks who came from industries that were not in materials research. In some ways, our problem has a different set of constraints than the normal ones, because in the end, our processes are controlled by fundamental physical laws, right? And so those provide interesting constraints on the AI problem in ways that are different than, yep, that looks like a cat on Facebook, right? And so, that's, I think, an interesting additional partnership that needs to happen between things.
That is so cool. A great way to actually help bring that together. Before I continue, I want to open up to everyone else to make sure, I don't know if Benji or Alexis, if anything else you want to touch on that front, talking about this real-time diagnostics and the system itself.
Yeah, actually, I think that's a really great point when you think about how those constraints, those physical constraints, and our understanding of the physics and the chemistry and the other, controlling factors of our system needs to be taken into account, right? And so it's one thing to have a system that can run a bunch of experiments and solve a single problem. But what we really want in terms of new knowledge is to understand what that relationship is. So why did changing knob A result in factor B being different? Why is this material performing better or worse because of a change in a parameter or something like that? And so linking that knowledge to the information that comes out of an autonomous system is a critical part of that. And that can be aided by the software and the AI systems that are part of the research system. So putting that all together in one package really allows for a lot more calculation, a lot more than we can do in our own minds, a lot more quickly.
Yeah, just to add on to that. So as Alexis and Eric were saying, you want to get away from the black box where the AI had some reason for making decisions, but it couldn't really explain it to the human. And maybe it was just based on statistics, but in science, what we want is we want the output to be scientific understanding, right? We want hypotheses, we want the ideal gas law or something like that. And what's great is, in the future, as we're going along and improving things, we want to move towards actual reasoning using artificial intelligence rather than statistical inference, which is more what we're relying on now. And so the interesting part about that is that that's now becoming the forefront in the domain of artificial intelligence. So it's very interesting because, when I first started doing this, I was like, well, the AI people have all kinds of super interesting, crazy problems. AlphaGo, they're doing amazing things. But all of those use large data sets and don't exactly explain why and don't output sort of specific strategies. Whereas in our domain, at the end, right, the ground truth is physics and chemistry. And so the folks that I talk to and we work with in artificial intelligence see this as a new area, as an exciting area for them to work in, because when you do something and you get a result out, it's for a reason. And the trick then is to figure out the reason for that. So doing the artificial intelligence reasoning, building the hypotheses, testing them, and figuring out, what actually happened. So we were pleasantly surprised that the artificial intelligence community is starting to find this area of materials research in particular as interesting and worthy of them to invest in.
So tapping into that community then and kind of talking about really going forward. So you talked a lot about how the system is going to work, talked a lot about the paper, where it's headed. But starting with you then, Eric, we're interested. What do we really need to bring a lot of what you've put in this paper to life? Like, how do we get to the next step to really capture everything we've talked about today?
Well, I think one of the hopes out of this publication was just to make sure that everyone, had a kind of a scope of the different problems that need to be dealt with, right? They span issues in human development, education. They span issues in the development of algorithms, the development of systems. And, the unfortunate comment that always happens with these things is you just need more money and more time. I mean, it's true, right? But the way that happens, right, is by attracting people to the ideas and generating communities of people who agree that these approaches are ones that can bring value. I mean, that's often the way that scientific progress moves, right? As communities come together and they come to a consensus on what the key problems are and the key approaches are. And I think to some extent, we're hoping that with this paper, as well as continuing activities that we have at conferences and things like that we develop a community of people that seek support from places like the National Science Foundation, the Department of Defense, the Department of Energy, in order to advance the goals. So I think that's part of it. But also, I think too, there's a real need for continued open communication around these things. I think, we talked some about the Aries Os as a way of plug and playing, but many of the tools that are used in material science to do the characterization and analysis, they're complex tools, but they're also proprietary tools, right? Companies sell them to you and they have, in some cases, constraints on how they give the data to you and the ways that you can manipulate that. So we're also making a bit of a call to say, hey, this all needs to be done with tools that are available for everyone. I think that's an important part too.
No, that makes perfect sense. I mean, making sure everyone has access to this is one of the biggest ways we've, touched on today about progressing it. But I want to make sure I open up to Alexis and Benji as well. Was there any thoughts that you had about how to really bring this to life, or at least bring it to the next level?
Yeah, I think one of the really important things that came out of the workshop, like Eric mentioned, is the community building and bringing the folks together who have the perspectives from computer science, from engineering, from material science, and also, from education and training and from the social sciences, right? Understanding how people work together and how humans and robots or other autonomous systems can interact. And sometimes as scientists, we speak different languages, use different terminologies, and the more we talk to each other, the better we can understand not just each other's languages, but what kinds of questions each group is asking and how we can help each other answer those questions.
And the floor is open for you then, Benji, if you have any other final thoughts on a topic of what the paper may need to keep going.
Really, just to say that I'm very excited. I think the energy around this area is great. I think people, when they start to look at it, they get it and they see the value and they become excited about it. I guess what I'm hoping is that we can broaden that community. And what was great is at the workshop, we had, representation from NSF, so Alexis, we had folks from Army, Navy, Air Force, DARPA, Department of Energy. So the government is clearly aware and engaged. And so I think this is really an exciting time. And I hope in some ways, just like the Industrial Revolution revolutionized how we do work, right? It leveraged our manual capabilities that what we're talking about today will start a research revolution where we're doing so much more and better research into areas that are, again, more accessible, that more inclusive, more diverse. All of those areas will really be helpful to society, and that's my sincere hope for it.
Very well put. And honestly, the research revolution, I think you may have just got the title for the podcast. I mean, that's awesome. I love that. And to kind of like bring this all to a head, then kind of distill it down. So I had my analogy earlier where I talked about having, like R2-D2 help me, my co-pilot, my X-Wing. I'm Luke Skywalker. He's able to fly the vessel for me so I can do research on the side, looking at star maps, whatever it may be, so we can work as partners. So in that case, as you know, a human and a robot working together, a system. So we kind of talked about how researchers can better refocus in different areas while these autonomous systems start to work. But starting with you then, Benji, how do you see the role of the human researcher changing as this research revolution kind of kicks into shape?
Right, absolutely. So one of the things that I do not see happening is that researchers are out of work, and that was something that was people would say to me, it's like, hey Benji, what are you doing? You're going to put us all out of work. And I guess my response was, nobody ever complained when we got more computing power, right? We just did more and better things with it, and now we have supercomputers that we put in our pockets and we call them phones. And so I think that and also that's maybe a good way to think about how humans and scientists and robot scientists can work together, is we don't even see the computer in our phone. We just talk to it and we say, hey, call Eric. You're not thinking about dialing the buttons, right? Pressing the buttons. You're thinking about, I want to talk to Eric, and you talk to your phone and it calls Eric. And so that same thing about really rebalancing the division of labor in the research enterprise to say, we have a partner, the research robot, who can do the heavy lifting, who can do the dangerous stuff, the dull stuff, the stuff that you have to do over and over again. But also at the same time, as you're saying, do that complex calculation in high dimensional space that computers are really good at. On the other hand, computers are not good at things like intuition, creativity, understanding, the societal impacts of everything. And so the human will always be a critical partner in this endeavor because we bring all of that makes it valuable. And so I think in the end, my hope is that, I don't know, a couple decades from now, we'll always be thinking, it's like, hey, I need my research robot to help me out with this because I want this to go really fast.
And I'll open the floor again to Alexis and Eric then to touch on your thoughts on the same question.
Yeah, I absolutely agree. I think having the human in the loop is always going to be part of how we work. The nature of jobs will change, but the people will remain essential. So maybe our roles will shift from being the operator or the laborer to being the programmer or sort of overseeing the effort. But I don't see any future where all of our jobs have been taken over by robots, but rather where we have the assistance that Benji described, similar to how we think of computing power now.
That makes sense. We want to make sure we dissuaded any worries that came up. So we really appreciate all your insights, thoughts, and covering what your paper is. It's a very cool, very enterprising view of the future. So we'll definitely be following up with you guys as this progresses. So we want to thank you all for joining us today. It's been such a pleasure speaking with you.
Our pleasure.
Thanks, Ken.
Thank you.
Thanks, Michelle.
Thank you very much for your time.
Make sure to follow us on social media at Facebook, Twitter, LinkedIn, Instagram, and YouTube at AF Research Lab. And remember, stay curious.
Logging off.